So far looking at chapter 3, 3.1, 3.2, 3.3, and then we put it all together, remember, in 3.5. We've been working with polynomial functions. So now we're backtracking. We're going to go to 3.4 here, but because we're looking at rational numbers now. And remember, many rational numbers, right, have restrictions where we're working with fractions and the denominator cannot be 0. So we'll go over, again, a recap of everything before we go over an example. So it'll be similar to 3.5. We're just adding in a little bit of steps that we're doing at the beginning of the question before we graph. So many rational functions have restrictions. So for example, those restrictions would be vertical asymptotes and horizontal asymptotes. And again, that's back in chapter 1. If you needed to go back and review any of that, we'll do a little bit of it here, but obviously not fully. So a vertical asymptote, obviously vertical would be up and down, right? Your function will never are crossed. So your vertical asymptote will never, you're drawing it, but it's imaginary. It will never cut through your function, your graph, your curve. So the function doesn't run through the vertical asymptote. It will occur at an x value, right? Vertical, we're looking at an x value that makes the denominator equal to 0 and the numerator equal to a non-zero value. A non-zero value, just to write in there, would be a number, right? So what we're talking about is we're going to have a number on top divided by 0. So a number and then divided by 0. And I'll write that out a little bit more. A rational function is undefined. Undefined meaning you would get an error on your calculator, right? So again, error, or we would say it does not exist. So that's what we're saying by undefined for a specified x value, where that vertical asymptote is. That value is undefined and does not exist. So if we were looking at, again, going back to chapter 1, if I was looking at a limit and x is approaching, I'm just going to say a value of a, right? A particular number, and I'm looking at a function. And I'm looking at the limit as we're approaching that value. Again, I'm going to have a number over 0. And if I end up with a number divided by 0, I will have a vertical asymptote. So I will have a vertical asymptote. And the limit does not exist, right? This limit, we already have it down there at the bottom, but the limit does not exist for that particular example. And again, this is back in chapter 1 if you needed to go back and review that a little bit first, maybe before you're doing this or during study hall. Whereas a horizontal asymptote, obviously vertical is running, this way, the horizontal one is running this way. They may cross your function. They may cross your graph. So I have a graph, my graph might cut through the horizontal asymptote. It does occur at a definite y value, which means I will get, I won't get that it doesn't exist. I will actually get a number for this, for which x values are approaching very large positive and or very large negative numbers. So like very large positive numbers is, let's say, plus infinity, right? Very large negative numbers would be approaching negative infinity, approaching. So this is the idea of if we're going all the way as far as we can to the right, all the way as far as we can to the left, we're for x values, right, along the x-axis, we're talking about the idea of end behaviors. So if I was to have, just looking at where to put this here, I guess over here, if I was to have a limit as x is approaching infinity, but let's say it's positive or negative infinity, right, for a function, I'm going to get a definite y value. So f of x is the same thing as y, right? I'm going to get an actual number. I will get a definite y value. So the limit does exist, is what we're saying here. The limit exists. When I'm analyzing rational functions, now using calculus, I have to include restrictions on the domain. So which one is the domain? When we just in the previous video got the domain and range, The domain is talking about my X values only, right? So this statement is just saying that I have to include restrictions on my X values only. So just the vertical asymptote restrictions. So if I want to write that out here, so just a matter of finding room. Just the vertical asymptote restrictions. So I'm only listing the restrictions for the X value, which would be for the vertical asymptotes, okay? So the critical numbers include restrictions on the domain with the critical numbers when finding intervals of increase or decrease. So this means that the first chart that I do, so like F prime of X chart, right? The first derivative chart that I'm doing, the test, will tell me my critical numbers and I can list the restrictions there, or the possible points of inflection. And when I'm finding concavity would be my second derivative chart, right? Is where I would find those answers and list if there's any restrictions. So here are the steps. Some of it is cut off here, so I am just going to clear this and move it up for a second before we do an example. So to sketch a graph of a rational function, basically 3 to 8 was the same as the last lesson that we did, right? 3.5, get your x-intercepts, figure out the critical numbers, determine my intervals of increase or decrease, the first chart, and determine intervals of concavity and points of inflection, the second chart, sketch it, state the domain and range. So 1 and 2 are the newer portions here that we're going to do in this video because we're also talking about rational functions. So I need to state any restrictions on the variable x, again, which is my vertical asymptote, and state any restrictions on the variable y, which is my horizontal asymptote. Talk about the behaviors that are happening around the asymptote, so looking at the limits, and then everything else is the same. So to look at that here, this example, analyze the following. You can see that this is a rational function. I have x divided by x minus 2, all square the denominator, and my function is f of x. So the first thing I want to do then is list my restrictions on x, right? So just to write this all out again, if we look forward here, I've got this whole page and the entire next page and another page. And looking at how much room I used, I basically filled it up. I had a little bit of room left on the last page just above the graph. And I kind of wrote conservatively to try to fit everything that I could on the page. So yeah, you want to try to make sure you're not writing too big there to fit everything in. Long questions, right? Okay, so number 1, restrictions on x. And I'm correlating number 1 with the step number 1, right? From the list of 8 steps. So restrictions on x. In order to do that, what are my restrictions? Well, the denominator, we don't want to be 0, right? Because then that would be my asymptote. So I can't have the x minus 2 squared cannot equal 0. So what's the actual value of x there? So when it's squared, it's just 2 of them, right? X minus 2 and another x minus 2. So that's the same thing as just figuring it out for one of them. So if I brought that negative 2 over, it'd be 0 plus 2. So therefore, x cannot equal 2, just twice, right? So what is happening here? In order to figure out my vertical asymptote, let's look at the limit of what's happening when I'm approaching 2. So what is the limit as x is approaching 2? Again, from chapter 1. I write out my original equation, x over x minus 2 squared, and I just plug in what I'm trying to figure out the limit of. So I plug in the value of 2 when I see x. So I would have 2 for the numerator. 2 minus 2 squared is, again, 0 squared. There we have our number divided by 0, which is where we say if I have a number divided by 0, let's just write that out, a number divided by 0, then I know that that limit does not exist, right? So we have a vertical asymptote is what we just figured out. So we have I'm just going to do this, okay? Vertical asymptote. So we have a vertical asymptote at x equals 2. So now, before I move on to y, let's just talk about the behaviors around the vertical asymptote. So that would be like step 2 here. The behaviors around what's happening around that vertical asymptote. So what I need to do is just simply look at my limits as x is approaching 2, but I need my 2 different directions. Remember, I've got my limit as I'm approaching 2 from the left side, right? So like if this was x equals 2, right? I'm going this way as I'm approaching from the left, and then as I'm approaching, if you remember, from the right, what is happening right before and let's say right after it. So let's do the limit as x is approaching 2. This indicates from the left. If you want to write that on the bottom underneath, from the left, write out my original equation, x minus 2 squared. And what I'm doing is from the left, if this was 2, right, on a number line, I'm just picking a number that's just to the left of 2. So literally I could pick a number like 1.999. So 1.999 for x. And then when I see x down below, 1.999 minus 2 squared. And for this, if you were to go back to the bullets on the first page there where we're talking about the vertical asymptote, if you remember, I need a definite value for y, but I don't need a definite value for x. All I care about is if it's going to be approaching positive or negative infinity. So for example, this number at the top is positive. I don't actually have to plug it into my calculator. You can if you want to, but you don't have to. And this would be a very, very small negative number, right? But then when I square it, it would be positive. So a positive divided by a positive would end up being that I would be approaching positive infinity. If you were to divide those numbers, you're going to get a very, very large number. So what we know then is as x is approaching 2 from the left, my y is going to be approaching positive infinity, way over there on the right. Or way up, sorry, vertically. As x is approaching, sorry, negative 2, x value negative 2, my y value is going to be very, very positive. Okay, let's approach from the left and see what happens. Sorry, from the right. My limit as x is approaching 2, sorry, from the right-hand side, starting at the right and narrowing in on 2. Again, I write out my original equation with my x's, and I simply pick a value again that's just to the right of 2. So a value just to the right of 2 could be, you know, what, 2.001. I wouldn't do 0.0000, right? I probably wouldn't make any more zeros than that, or 2.01. All over, again, I see x, 2.001 minus 2 squared. And again, I'm using my x's. I don't need a definite value. I just need to know whether I'm positive or negative. So here I would have the numerator is positive. Here I would have still a positive number squared, so a positive number. So this one is actually going to be approaching positive infinity as well. So what I'm learning here is as x is approaching 2 from the right side, so I've got approaching from the left, approaching from the right, what's my result? My y is actually going to be approaching positive infinity as well, way, way up vertically on the y-axis as well. So to figure out my horizontal asymptote, so basically to go back to number 1 again, I figured out my vertical asymptote. So if I just say, if you hopefully understand why I'm writing number 1 again, we're going back here. To help with the horizontal asymptote, let's look at our end behaviors. To help with, again, I'm just going to do this horizontal asymptote for short. To help with my horizontal asymptote, which will figure out my restrictions on y. Okay, so I'm gonna have to, I don't know if I can fit all of this in here. I might have to move it eventually, so stay with me. So what I'm looking at with y is I'm looking at the limit, right? when x approaches infinity from the left, and then we'll be looking at negative infinity, then we'll be looking at positive infinity. So the limit when x is approaching negative infinity, so again, x is approaching negative infinity, so I'm moving like as far left as I can, and I write out my original equation. So if I'm way over there on the left-hand side for the x-axis, I'm just choosing any large negative value. So I mean, way over there, you could get, you know, -1 million, -1 billion. We don't need to go that large. So I'm just going to write down here, you want to choose a large negative value, but it doesn't need to be ridiculously large because that's just going to be more work for you, right? So just for example, I'll pick -1,000 is fine. So if I'm picking x as -1,000, again, plug in -1,000 down below, but then I'm going to be minusing 2 and squaring it. And then if you remember, again, if you go look at the bullets under horizontal asymptote on the page preceding this, I do need a definite value. So I do want to plug these into a calculator and get an actual value for this. So I end up with, just write down what I have here. I have -1,000 over, I ended up with 2,3,004,004, 1,004,004. And that gave me a value close to, I cut it off a little bit, so that's why I put the dot on top. Negative, obviously, 0.1230, 996. So what this is saying is, let's go back to the beginning. As x keeps getting closer and closer to negative infinity, right? My y value, my answer here, my y value is going to be very, very close to 0, but negative coming from below. So I'm nearing, let's just write this out here in a different color. So I'm nearing a y value of 0, but from below. From below 0, going up to 0, approaching, right? But not touching yet. And let's look at the next limit then. Don't know if I can fit this in, hopefully. The limit as x is, we're going all the way to the right, to positive infinity. Again, we write out what our equation is from up above, our function. So same thing here, I'm going to pick a very, very positive value. So if I had -1,000 here, I might as well just pick 1,000 here, but positive, right? Because we're on the positive side. We're to the right of 0 on the x-axis. And we put 1,000 minus 2 squared. And again, I need to actually figure out what that is. I need to use my calculator and compute this. So that's 998 squared. I have 996,004 and 4. And that's going to be equaling approximately 0.001004. So again, as x is getting closer, like moving more and more over on the right-hand side, approaching positive infinity, my y value is again approaching 0, getting very, very close to 0, but from up above. So we will write that out. I'll write it out still in green here. So as x approaches negative infinity, my first one here, as x is approaching negative infinity, y is approaching 0, but y is approaching 0 here. This negative means from below, right? But then as x is approaching positive infinity, my y is approaching 0, but from above. So again, that plus means I can fit that in there and you can see it from above. Okay, so therefore, I'm just going to put my therefore over here. Hopefully you have a little bit of room underneath there. Therefore, my horizontal asymptote then, right, is at y equals 0, because I'm approaching 0 from below, I'm approaching 0 from above. If I'm not actually hitting 0, that's because there is a horizontal asymptote there at y equals 0. So the next would be, just looking at what number that is to get my intercepts. So we're on number 3 now to get my intercepts. I'm just gonna keep it here. So number 3, my intercepts. So again, to get your x-intercept, I'm going to let y equal 0. So this would be y, right? So let 0 equal the right-hand side, x over x minus 2 squared. So here again, if you were to cross multiply, you'd end up with 0 times the denominator, which is just 0, equaling x. Well, that was easy, right? So therefore, if y is 0, x is 0. So therefore, I have the point 0, 0. So my x-intercept is 0. So now for my y-intercept, I'm going to let x now equal 0. So I'm going to leave f of x to be y. But when I see x, 0 over 0 minus 2 squared. Negative 2 squared is 4. So 0 divided by 4 still gives me 0. Be careful, that one's not an error, right? If you think you might make a mistake, just make sure you're plugging it into the calculator then. If 0 is at the denominator, it does not exist to get an error. But if 0 is on top, 0 divided by anything is actually 0. So I have the same point. When x equals 0, y is equaling 0. So therefore my y-intercept is 0 and I have the same point. So I have one point there on the graph that I can draw, a little bit of information. Now let's do our critical numbers. Just looking ahead here. So we'll do our critical numbers, which is to get the first derivative and do the first derivative test with the chart. And then I think to move on, we'll just kind of cut the video so it's not so long and just continue it with another video. So let's do that for now. Let's get our critical numbers. So our critical numbers is number 4. And then number 5 would be the chart. So how do I find out my critical numbers? I need to get the derivative, right? So I've got the original function here, so I don't necessarily have to write it out again. If you like to have it beside it, you can go ahead and write it out again. That way it's closer to you to see when you are manipulating it to get the derivative. So to get f prime of x, we're going to do just to write out, just to tell you, you don't have to necessarily write this out, but when I have a numerator and a denominator, right, a rational number, I do the quotient rule. So again, the quotient rule is, again, I'm just doing short form here, the derivative of the top times the bottom exactly the way it is, and then minus, remember if you go back to the quotient rule, the derivative of the bottom, and then multiplied by the top exactly the way the top is. Okay, so let's follow that. So to get the derivative, we have here derivative of the top. So that would just be 1, right? Times the bottom, x minus 2 squared, subtract. Okay, that part was pretty easy. The derivative of the bottom. So the derivative of the bottom, the 2 is going to come out in front, or here, the 2 is going to come out in front. X minus 2, sorry, to the exponent of 1, but I don't really need to put that in there, right? But I also have to do the derivative of the inside. So the derivative of the inside is just going to be 1, but I should still write that down when I'm marking you, so I know that you've analyzed that and you're looking at the derivative of the inside, and then multiply it by the top. We haven't done that yet. And then multiply it by x, right? And then all over, I didn't write that down over here. I was just talking about the numerator, but then it's all over the denominator squared, right? So just make sure that you have that. So I have x minus 2 squared is my original, and then that with square brackets has to be squared. Then it's just a matter of cleaning this up. So 1 times that, right? Just the 1 can go away. So I'm ending up with x minus 2 squared. And then here I have a negative 2 times a 1, negative 2, and then times an x. So I can just turn that into negative 2x x minus 2, just so there's a little bit less going on there. And then at the bottom, if you remember, I have one base, two exponents beside each other with a bracket in between them. I multiply them, right? So then I would end up with x minus 2 to the power of 4. Now, is there anything I can do? What we've done in the past, if you remember, is I'm kind of looking to see if I can factor, meaning to common factor. And a term is separated by a plus or minus sign, right? So I have an x minus 2 squared here. Then now this is an entirely new term. 2x, negative 2x, and an x minus 2. So I have an x minus 2 that's common that I could pull out. And then I might want to put square brackets here. So I have x minus 2 squared. So I still have 1 left for the first term. And then minus 2x, because I pulled out this x minus 2 over x minus 2 to the power of 4. So then cleaning up inside the bracket here, that would just be x minus 2 without brackets minus 2x, right? Just looking at where I should put this. I'll go over here. So then I have x minus 2, and then I have x minus 2 minus 2x. So 1x, take away 2x would be a negative 1x or negative x minus 2. Hopefully you follow where that came from. Now, is there anything I can do? What do you think? I have an x minus 2 to an exponent of 1 and an x minus 2 to an exponent of 4. So I could eliminate this one and eliminate one of these, right? And I'd be left with the negative x minus 2, or at this point I didn't even have to put it in brackets, over an x minus 2 cubed, because I've eliminated 1 with the numerator. And that narrows it down pretty good. And then here, just to indicate, I'm just saying I'm moving this now over here to continue on. That's all I mean by that. Set it equal to 0, right? I need to get my critical numbers is to set the first derivative. So there's my first derivative equal to 0. And then I am essentially just copying out what was over here. But then if I make it equal to 0, again, cross multiplying, that times 0, basically I'm just setting 0 equal to the numerator. So that makes it look a lot better. And then if I were to bring that negative x over to make it positive x, 0 plus x would just be a positive x equaling, careful because it's still a negative 2 that's over there, right? So there we go. I only have a critical number. So therefore, I have a critical number at x equals negative 2. So I have found my critical number, number 4, but now we're moving into number 5, remember? And then we'll take a break. Determine the intervals of increase and decrease and classify the critical numbers would be to be doing the chart. So this is now, step 5. So I have a critical number at x equals negative 2, just because I'm going to be clearing this. We should be on the second page somewhere now. So that was just to double check, step 5. Yes, is where we're headed right now, is what I mean. So step 5, we're going to do our chart with our one critical number. Now I want you to just pay extra close attention here because yes, I have negative 2, but then don't forget, isn't this my x-axis here when I label it, right? This is my x-axis, this is positive infinity, and this is, I always don't leave enough room there, negative infinity. If we're talking about the x-axis, we've already determined in number 1 that I have a vertical asymptote. So that affects the x-axis, right? So that vertical asymptote, just right down here, I have an x restriction. I have a vertical asymptote at positive 2. So I want to include that in here. Okay, so this is my critical number, Cn, critical number, and this is my vertical asymptote. So I am going to include both of those on here. So now that affects my intervals. So now I have 1, 2, 3 intervals, right? So again, I'm going to have a 4-column chart then. So the first column is my factors of f prime of x. And then my intervals. So from -infinity to -2, from -2 to +2, and from 2 to +infinity. And then I need to go back to my previous page to list my factors of f prime of x. So my factors of f prime of x are both the numerator and the denominator, let's say right before you set it equal to 0. So I'm just going to copy that out for you here. So where I put that kind of burgundy maroon circle, it looked like this. We got down to -x minus 2. I think I still had brackets at that point, over x minus 2 cubed. And then the next step was setting it equal to 0. Okay, so my factors of f prime of x are again the numerator, which is -x minus 2, and then the denominator, x minus 2 cubed. And then this is the first chart, the first derivative chart. So we need our overall sign of f prime of x of the derivative. I just don't write the word sign down. And then we have whether this is increasing or decreasing along our original function, right? So let's go ahead and fill this out. We should be pretty good at doing this by now. There's one new thing to point out in the chart here. So again, just pay attention. I have to pick a number less than -2. So let's say -3. So if I pick -3 minus 2, careful here, -x, -3 ends up being a +3, right? Be careful there, -2, so that's a positive answer. -3 here, -2, -5 cubed, a negative times a negative times a negative is going to be a negative. And then here when I'm looking at my overall, I was multiplying them, right? But don't forget that this was, it's a quotient. So what I'm looking at is a positive divided by a negative this time, which is the same result, but just I'm looking at dividing instead of multiplying. So that would result in a negative answer. So that would mean that I'm decreasing along this part of the function in this interval. Between -2 and 2, 0 is right in the middle there. -0 minus 2 is going to be negative. 0, -2. So again, -2 cubed, though, is going to be negative. And negative divided by a negative is going to be a positive. So I have an increase here. If you can't fit it, that's fine. Just short form it. And between 2 and infinity, again, I could pick the number 3. Now be careful, this would be a -3 minus 2, so that would be a negative. 3 minus 2 is just 1 cubed, so now I'm positive. So if I have a negative divided by a positive, I'm still going to end up with a negative though, and now I'm decreasing. Okay. So let's look at what this is telling me. So again, if I'm decreasing all the way from -infinity, starting reading the graph from left to right, I'm decreasing until I get to -2. -2 something is happening, and then I'm increasing. Then this would be my local min, right? So here I have a local, right here at this point, I have a local min at x equals -2 on either side. That was my critical number, right? But look at what's happening here. Be careful. This is not a critical number. So at 2, what is happening? This is my vertical asymptote. So it's not a local max or min. So just to point that out, it's not a local max or min, because you could see here easily, I'm increasing, then I'm decreasing. You would have called this a maximum point, right? But just be careful to go back and look up here that 2 was not a critical number. We're just indicating that that's a vertical asymptote happening there. So I have my local max, my x value. I need to figure out my y value so I can list my conclusion of where I'm increasing and or decreasing. So I have here a local, we said min, at x equals, and it was -2, right? -2. And then I need to sub that into my original function. We don't even have the original function on this page, so we might want to write that out over somewhere. F of x equals x divided by x minus 2 squared. Okay, so f at -2 would equal -2 on top divided by -2 minus 2 squared would be -2 over -4 squared would be +16, which lowest terms would be -1/8. So therefore, my local minimum is at the point of -2, -1/8 is what I found out there. And then just to state, increasing and decreasing. My function, my original function, right, f of x is increasing where? F of x is increasing when? Here, I'm increasing between -2 and 2. So between, when x is between -2 and 2, and my original function is decreasing when x is less than, because we're not going to include these numbers, right? So when x is less than -2, and decreasing when x is greater than +2. Okay, so what I've just found is my local extrema. And like I said, we'll just break this up into 2 videos. And so now we're going to be headed into step number 6.